In this video, I'm going to be talking about the electron dot notation, or in other words, what we use to identify the valence electrons of an atom. All right, let's get started. Number one, lithium. When I look at lithium, we're going to look at our periodic table. One thing you'll notice is, well, you may not be able to see it very well, but each row on the periodic table has a number correlated to it. So this one is number 1, number 2. These are 3 through 12. This is 13 or 3A, 14 or 4A, 15 or 5A, 16 or 6A, 17 or 7A, and then 18 or 8A are my rows on the periodic table. These rows also correlate to the valence electrons. For example, this entire row is only one valence electron. This entire row is only two valence electrons. Over here, this entire row is 3 valence electrons. This one's 4, 5, 6, this one's 7, and this one's 8. When we look at those electron configurations of these, the valence electrons come from the s orbital and the p orbital. Those are your valence electrons. The D level and the F level are more on the inner side, and they don't really come out as valence electrons. Our valence electrons in an atom come from our s orbital and our p orbital. Back to number 1, lithium. Lithium, since it's in this first row, only has one valence electron. So for this one, all you're going to do is you're going to put 1 dot beside it. That is the electron dot notation for lithium. Let's go on to the next one. This next one is boron. Boron has 5 electrons, but if we're looking, this is on row 13 or 3A. We go here, this one has 1, 2, 3. Boron has 3 valence electrons. Now when it comes to 3 valence electrons, so these 2 electrons, this is as if we're filling up that s orbital. S orbital can only hold 2 electrons, whereas the p orbital can hold up to 6. So when we're writing our electron dot notation, we do these 2 first, then when it comes to the next one, then we go up here. We're basically going to go in a circle, but we're going to go every other when we get to higher valence electrons. But for now, boron only has 3. So that is the electron dot notation for boron. This next one, oxygen. We're going to look here at our periodic table. Oxygen has 8 electrons, but we're more focused on the valence electrons. I don't know if you can see it, but this is in row 6A or 16. It's going to have 6 valence electrons. But if we're counting, these ones have 1, this one has 2, 3, 4, 5, 6. Oxygen. Oxygen has 6 valence electrons. So like I said before, we're first going to fill up, quote unquote, the s orbital. So we're going to have 1 valence electron there and 1 there. Since we know that it has 6 valence electrons and we've already done 2, we need to do 4 more. We're going to go here, but now that we've filled up our s orbital, we got to fill up our p orbital. But if you remember from our orbital notation, you have to do every other going up in the same direction. In this case, electron dot notation does the same. We're not going to put 2 up here. Well, not yet anyway. We're going to next go to the side. There's 4 electrons, 5 electrons, and now 6 electrons. We do every other after we fill up our s orbital. All right, so that is the electron dot notation for oxygen. Let's look at neon. Now, neon's a noble gas. Neon is over here. It has 10 electrons total, but since it's in this last row, its valence electrons are 8. It has 8 valence electrons. So we're going to put our first 2 here as if to fill up our s orbital. Then we're going to go every other. There's 4, 5, 6, 7, and 8. Yes, neon will end up being completely filled, and that's actually one of the reasons why it's called a noble gas. Its valence electron, or last outer shell, is completely full. That's why it has the name noble gas. All right, let's look at magnesium. Magnesium has a total of 12 electrons, but we're more focused on the valence right now. That one has 2. This row has 1, this row has 2. So all we're going to do is put our valence electron there and our valence electron there. Let's look at another one. Phosphorus. Phosphorus, its electrons are 15. It's in the row 5. So it's going to have 5 valence electrons. We're going to fill up our s orbital first. 1, 2, 3, 4, 5. We have our 5 valence electrons. All right, let's do a couple more. Chlorine. Chlorine has a total of 17 electrons, but we're focused on the valence electrons. It's in group 17, row 7A. So it has 7 valence electrons. So we're going to go 1, 2 to fill up our s orbital, 3, 4, 5, 6, 7. That is the electron dot notation for chlorine. Now let's look at silicone. Silicone, if you're looking at our periodic table, is here. It has 14 electrons, but it's in group 14. So we're going to have 4 valence electrons in total. We're going to start off with our s orbital, fill that up first, then we're going to go to the top and then to the right. Next we have iodine. Iodine has 53 electrons, but it's right next to the noble gas, so it's going to have 7 valence electrons. So we go 1, 2, fill up our s orbital, 3, 4, 5, 6, 7. There's the electron dot notation for iodine. And last but not least, for this part anyway, we have aluminum. Aluminum is number 13 on the periodic table. It has 13 electrons. But we're looking at the valence electrons. It's part of group 3, 3A or 13. So it's going to have 3 valence electrons. 1, 2, 3. Now that's great, the electron dot notation for normal atoms. But what happens if they become ions? By that I mean we have 2 types of ions. We have cations, which are positively charged, and anions, which are negatively charged. So let's take a look at what would happen if we added or subtracted some electrons. For example, our lithium. Lithium, we're going to get rid of one of those electrons. Remember, electrons are more negatively charged. So when we get rid of a negatively charged electron, this atom is going to end up more positively charged. So if we get rid of lithium's 1 valence electron, we're going to end up with Li and no electrons around it, because we got rid of the 1, is going to be plus. You can either write it as that, because it's understood that it's only one positive charge, or you could end up writing like this, 1 plus. Either one is correct. All right, so let's look at boron. If we were to do boron, it looks like we're going to subtract 3 electrons. Keep in mind, electrons are negatively charged, and if we're getting rid of 3, this is going to be a more positively charged atom. Boron, if we get rid of its 3 valence electrons, it ends up with 0 valence electrons. So it's going to be a more positively charged, but because we didn't just get rid of 1 electron, we got rid of 3. We're going to do a 3 plus. And that's the notation for boron. Ionized boron. Both of these so far are known as cations because they are positively charged. Now let's look at this one. Oxygen. It currently has 6 valence electrons. But if we add 2 more negatively charged electrons, it's going to become a more negative ion. So we have oxygen. If we add 2 electrons, we're going to keep our dots from our last one, but we add 2. So the electrons are going to get added to our oxygen. This is going to mean we're going to have a negatively charged, a -2 charge on our oxygen. This one is known as an anion. Positively charged are cations, whereas negatively charged are anions. Now let's look at gallium. Gallium has 3 valence electrons, and in this instance, we're getting rid of those 3. So we're going to put our brackets. We're going to have no valence electrons around them, brackets, and if we're getting rid of negative, it's going to be more positive. So we're going to do a 3 plus. This one is also a cation. Now let's look at magnesium. Magnesium, we have 2 valence electrons, and if we were to get rid of 2 electrons, we would just have magnesium with a +2 charge. This one is a cation as well because we are losing electrons, losing our negative factor. Phosphorus. So phosphorus, we have a total of 5 valence electrons. And with these 5, it looks like we're going to add 3 electrons. These electrons are going to end up going around the phosphorus. So we have our phosphorus, we have 1, 2, 3, 4, 5, but we add 3, so now we've got 8 valence electrons here. But since we added 3 more negative electrons, we're going to end up with a -3 charge. This one is known as an anion. This next one, chlorine. Chlorine currently has 7 valence electrons. We're going to add another negative electron. It's going to be chlorine with our dots. It's going to fill up. And that's going to be a negative. Now, like our lithium up at the top here, you can either write it as just a negative, or since we have since we understand that this is a 1 there, you could write it as this, Most people tend to write it with just the negative. The 1 is understood in this instance. And this one is going to be an anion. Now don't do what I did here. I just added 2 dots on each side. Don't do that. That'll mess you up. Do it like I did the second time, where you do the 2, 1, 1, 1, 2, 2, 2. Okay? Number 8, iodine. Iodine plus another negative electron. You're going to have the brackets, put the I, we're going to add another one. 1, 2, 3, 4, 5, 6, 7, 8. We get a total of 8 valence electrons. And like you did with the chlorine, you can either write it without the 1 or with the 1. Either one, as long as it's only 1 that it makes up the charge. This one is also an anion. We'll do 2 more. Now we've got silicone. Silicone's valence electrons are 4. Looks like we're going to subtract 4. So we're going to take away 4 negatively charged electrons. So we have our brackets, silicone. There's no dots around it because we took them away. And this is a 4 plus. It's going to be a positively charged. That means it's going to be a cation. Let's do one more. We've got aluminum. Aluminum has a valence electrons of 3. Now it looks like here we're taking away our valence electrons, the 3 valence electrons. So we're going to end up with, all by itself, with a 3 positively charged. This one is also going to be a cation. And this has been a video talking about electron dot notation of atoms and of ions.